Welcome back, Contemporary Math. We are in chapter 7D. This chapter is titled Assessing Risk. So I just wanted to talk maybe a little bit about what we're doing in the last section with expected value. So when we make decisions in life, typically what we do is we sort of weigh the rewards and consequences of our decisions. And so a lot of that you can kind of think about as being expected value. But there's not always a real definitive sort of way to put a number to a reward or a consequence like we did with the expected value. So it is more sort of generalized, and you do have to kind of interpret things for yourself. And perspective and the individual sort of preferences also come into play, right? There's a lot of things that come into play when we make decisions in life. But one of those things is assessing the risk or assessing the consequences of our actions, right? And so this chapter is about a lot of statistics that they're taking from basically reality. We're going to talk about some pretty heavy numbers. We're going to talk about risk and travel, what the accident and death rate, talk about the leading causes of death in the U.S. We're going to talk about life expectancy and things dealing with life and death in this section. So first thing they talk about is traveling, and they set up a kind of silly scenario in the book, and they talk about how dangerous basically driving a car is. But we're all sort of willing to take this risk of driving cars out there because we got to get around somehow, basically, right? It's expected of us, and the reward is worth the sort of the weight of the consequence is what we kind of decide for ourselves. So with risk and travel, travel risk is often expressed in terms of accident rate or death rate. So if we have an annual accident rate of 750 accidents per 100,000 people, this gives a relative frequency or probability of a person getting in an accident within a year is going to be 0.0075. And so we can kind of judge on like how dangerous things are, like riding in a car versus flying in a plane. We can talk about how dangerous things have been through the past and how they have changed. So this graph I grabbed out of the book, and we want to talk about example 1 says the following figure shows the number of automobile fatalities and the total number of vehicle miles driven among all Americans for each year over a period of more than 4 decades. In terms of the death rate per 100 million vehicles driven, how has the risk of driving changed over this period? So if I'm being honest, this is, let's see if I can go a little bit closer on this thing. Okay, so this is a bit of an odd sort of graph, and the way that they do it is a bit different. It works the way they have these figures. It gets the point across that they're trying to get across, I think. Let's see if I can get closer. Just a little closer. Just so we can kind of understand this thing. On the left over here, we have deaths. So the first thing, I want you to ignore the blue line. All I see are these boxes, these orange boxes. I see my year, and I see the number of deaths. So these boxes represent the number of deaths per the year. We're not looking at the blue line. We're not looking at these numbers. So what they did is they superimposed one graph over another, basically. So if we look at the orange boxes, around 1970, I'm getting around 50,000 deaths. Around 2016, it is right below, what, 40,000 deaths? I think in the book it said 38. I just rounded things to the nearest 10,000, to be honest. I was really lazy when I picked my figures. And they came out really close to what the book had, so I think I'll be all right. The other thing, we're going to ignore the orange boxes. We're just going to look at that blue line, and we're going to look at the numbers on the right over there. So we're looking at the bottom, tells us the year. The numbers on the right tell us the number of vehicle miles driven in trillions. So that is a number in trillions. Okay, so this graph shows the annual automobile fatalities in bars and vehicle miles driven in line in the U.S. And I get from the National Transportation Safety Board, apparently. So they cited their sources properly. 1970. So here's a little reminder. You have got a paper to let's do where you have to cite proper sources on. So that might be a good time to like throw that out there. Don't forget about your paper. We're doing 1970. I was really lazy and I said I want to do 50,000 deaths. I just rounded it to the nearest 1,000. And this is over 1.2 trillion miles. So if I'm looking at 1970, the orange box is giving me the 50K. The blue line down here is really close to 1.2. Okay, so the way they want us to express the death rate is deaths per 100 million miles driven. So I got 1.2 trillion miles. What I did is I 50K up top. Miles, 1.2 trillion. 1 trillion, 200 billion. Ooh, no, I'm missing 3 zeros. Sorry. So this is thousands, millions, billions, and trillions. So I got 1 trillion, 200 billion. This is my millions, thousands, and going down to my ones. Okay, so if I expand this and I want 100 million. So there are a few ways to do this, but if I want 100 million miles, $100 million miles is going to give me 6 spaces will give me a million. If I want 100 million, that's 8 decimal spaces. So if I move this thing 8 decimal spaces, I'm going to from small to big. So I'm dividing this thing by 8 decimal places is what I'm doing. So if I divide this thing by 8 decimal places, I'm going to end up with 12,000 on the bottom and 50 on top. So we need to convert miles to 100 million miles. We do that by taking away 8 zeros, basically. Okay, so I have this figure. This is my 1970 figure. I am doing basically 50 over 12 if we look at the zeros. And it should be giving me somewhere around 4.167 is what I got when I plugged in these numbers. Miles is what I should say. 100 million miles. Sorry. Got the last word there. Probably make that plural. Deaths per 100 million miles. Okay, so we're getting about 4 deaths. If we want to look at 2016 data, it's giving me about 40,000 deaths, and there are about 2.4 trillion. I'm grabbing this off the chart. This is the orange box. This is giving me this with the numbers to the left. It's pretty close to the 40. If I look over here at the right, this is, oh, no, sorry, 2016. And then I look over at the right. Where am I at? 2016, I look over at the right. It should be between and got the wrong number. This should be 3.2. Sorry, wrote the wrong number. 2016. I got 40,000 deaths. I'm going to divide this by about 3.2 trillion miles. Again, we want to convert 3.2 trillion to 100 million. We did that previously. 40,000 deaths. Or want to say 40,000. Sorry, I think I said the wrong number. So we got around 40,000 deaths. If we want to convert 3.2, I don't want to spend a lot more time doing this, but it should give me around 100 million miles. So I'm jumping a little bit on this because if I go 50 over 1.2, you might notice this 1.2 in the end becomes 12,000. So I'm jumping a little bit with this. If I start with 3.2 on the bottom, I'm going to end up jumping to 32,000. So what I'm going to end up doing is actually dividing 40 over 32, and I'll be getting somewhere around 1.5, right? And so I'm talking about 1.25 deaths per 100 million miles. Okay. And so you might notice we're going from about 4 deaths to about 1.25. It is going down pretty large, right? Pretty large amount. Which should make sense. There's been a lot of improvements in cars since 1970. It used to be the car would survive and the person not so much, and it's kind of turned around. Now the cars don't last quite as long, but the people last a little bit better. So I think that's probably the right direction to go in. For the 5-year period of 2012 to 2016, U.S. commercial airlines flew about 8 billion miles per year and had a total of only 5 crash-related fatalities, or an average mean of 1 death per year. Use these numbers to calculate the death rate per mile of air travel. Compare the risk of flying to the risk of driving. So I don't really like the way they did things in the book because they put things in different units. And when we want to compare things, we probably want things in the same units. So we want 5 crash-related fatalities. So there are 5. Every 8. So if we have 8 billion, and I want to do this to 100 million, the way I convert miles to 100 million miles is by dividing by 8 decimal spots. So 3, 6, 7, 8 would give me 80 here, or I'm doing 5 over 80 or 1/16, I believe is what this is going to give me. This is going to give me 0.0625. And so if we're comparing 0.0625 deaths per 100, the same units. And if we go and look back at our previous results, 0.0625 is a really small fractional amount compared to a whole number 4, right? And a whole number of 1.25. So like flying, when we compare flying with the amount of miles that we're driving, or comparing the deaths to the number of miles with flying and with driving, flying is way safer, right? So it's one of those things. We're just used to driving, so it seems it seems like it's something we should do more probably, but it is definitely a lot more dangerous than getting in a metal tube and going screeching across the sky, which seems crazy a little bit when you're on the plane probably, and it's turbulence and things, people freak out. So it definitely taps into your instincts there sometimes, but it is actually safer than driving, right? I would fly. Well, I can't say that. I do prefer driving, actually. You get to see everything. But it is not safer. I would feel safer flying than driving in general. Assume an approximate U.S. population of 325 million. Use this table, 7.5, to find and compare death rate per person and per 100,000 people for heart disease. Oh, I didn't realize it said this. I don't want to do per 100,000. I just want to do per person. The little thing in there. So I want to find for heart disease, accidents, and cancer, and find how many deaths per person this represents. And then after that, I want to find the US population is now closer to 328. So I want to find something, this is a little bit of a real number, but there are 256,162 deaths currently from COVID. And there's a population of 328. I wanted to compare that to these causes of death. So these are what we refer to as vital statistics. These are the leading causes of death in the US. This table is from 2015. So this table is already 5 years old when I'm making this video. It's probably going to be older by the time I stop using this video. So let's go here. This is 325 million is our US population. So if we want to know heart disease accounts for 300. If I want to go over the population, which is 325 million. If I want to know deaths per person, I divide these two numbers and I should be getting something around 0.00189. If we wanted to do it by 100,000, we would have to move this decimal 5 places. So it would be 189 deaths per 100,000 people. So I rounded these things, I believe I rounded them all to 5 decimal places. So I should be using approximate sign. Correct. Now we're talking about accidents, crashes. Per person. There were 136, 100. And if I divide these two numbers, I get 3 zeros. So we would probably expect this to be a lower proportion. We are talking about 600K versus 100K. So that is what do we get? If we multiplied it by 5 zeros, we would get 42 deaths per 100,000 people. I did heart disease, I did accidents. I want to do cancer next. So cancer has around 591, 100 deaths, over to 325 deaths per people. So if I want this one, this is around 0.00182. And this is deaths per person. So that would be like all forms of cancer. So that is probably including a lot of different forms. All right, so the last thing, I think was probably a little more relevant nowadays. Well, I guess they're all relevant, but this thing is really relevant. Going to COVID-19, it is 162. Population is 28 million. It's pretty close. It's a little over. But if I get this number 0 point, this is 1, 2, 3, 7, 8 deaths per person. And that's the current rate. And so that is definitely more than accidents and crashes. It's a bit less than cancer, right? But according to their chart, it does look like it would be, we're talking about 200K. It is ranking up there, right? For a single disease, it's pretty high up there. It's only under 2 things on that chart. So, not trying to harp on it too much, right? But like right now, I think your decisions have consequences. And I hope you make good decisions, right? I don't want you to make bad decisions in your life and then have to deal with the consequences of those things, right? It is a serious disease and we should take it seriously. All right, so now we want to talk a little bit about life expectancy. And we got 2 problems dealing with life expectancy. And then I'm just going to talk briefly about their little case study thing that they talk about in the book. But life expectancy is the number of additional years a person is given at an age. And they can expect to live on average. So life expectancy at birth is the life expectancy of a newborn infant. So we will look at both of these things in death rate, U.S. death rate by age 0 to 80. This gives us the life expectancy by age 0 to 100. So I changed the numbers around a little bit. I want to know how long finally life expectancy for a 10-year-old and an 80-year-old American. And this was in 2016 when they pulled these figures. A 10-year-old, if we look at this thing, we're looking at 10. It looks like they can expect to live about 70 years. So if they're living 70 years and they're already 10 years old, they expect to live to the age of 80. A 80-year-old if we look at 80, they're not expected to live as long because they're older, but here we go. It's about 10 years. So they're about 10 years and they're already 80, so they're going to live about 290 years. Okay, so then the question that they ask, are these consistent? Do they make sense? So we look at someone who's 10 years old and we're looking at they're expected to live to 80 years old. But we look at someone who's already 80 and they're expected to live to 90. So a part of this is an 80-year-old is expected to live longer in part because they're already 80 years old, right? So they've made it this far. They're probably going to continue to make it a bit farther. So this would be kind of like the probability that they make it to 80, they will live about 10 years longer, right? And so there are a lot of causes of death that like impact people that are younger than 80 that these 80-year-olds are not going to account for, right? They're probably going to be less active, so that probably plays into it as well. They're not putting themselves, what do I say? They're not like putting themselves as a target for a lot of things like a lot of youngsters. people might be. And so the other thing that they mentioned in the book is that this is also based off of the current data and the current health that exists and the current technology that exists, right? Well, along with medical advancements and other things like that, these things can absolutely change. And if we have medical advancements, there's a good chance a 10-year-old would live longer, right? And so speaking probably more in general and not showing you any facts or figures, but from what I understand is the average lifespan of a human has always been about 80. The reason why it's gone up, or the lifespan has gone up, is largely because we have dealt with things like infant death, right? We have made medical advancements that have really kind of curbed people dying at young ages. And so with that, your average lifespan does go up, but in general, people aren't really living a lot longer, right? We're all living around 80. Those that make it to like 40 had a significant, like a great significant chance of making it to 80 if you made it past like your 20s and 30s usually. It's like the longer you lived, the longer you were kind of expected to live, right? And to some degree. There were a lot of things that were knocking people out at early age, and which would drop your average life expectancy. We are also extending life a little bit. So if we look at this is the changes in life expectancy at birth since the beginning of the 20th century. So we look at 1900, and they want to go in the 20th century is 1900 to 2000. So we want to use the figure above to estimate the rise in U.S. life expectancy at birth during the 20th century. So if we look at the bluest females, it looks like we're going from about 50 to about 80. And males look like they're going from about, I don't know, 45 to 75. I think they're about the same. The book is really kind of precise. But either way, I think we're going about 30 years more. There's 30 years more life expectancy for every, and we're going from 1900 to 2000, so that's 100 years. So we are increasing 30 years over 100 years. And this is referring to life, and this is referring to your birthday. Or we're getting about 0.3 years of life for every 1 year birthday. 1 year birthday. I'm running out of room over here, but I get it. Every 1 year. Okay. Okay, and then they ask a silly question. They're like, well, what would your life expectancy be for a child born in the year 2100? Okay, so if we are born in the year 2100 and females are 80 here, we're going 80 plus 30, another 30 years is going to give us 110 years for female. And then if we do it, male would be like 75 plus 30. I think we're getting at what, 105 mil. So somewhere in that ballpark. Is it going to go at the same rate? We don't know. We don't know what our medical advancements, or if there's some disease that comes along, could change it as well, right? And so the last thing they talk about is the case study, life expectancy and Social Security. So they make brief mention like, well, our life expectancy is going up. That puts a strain on Social Security and Social Security budgeting. So people are living longer and it's putting a strain on Social Security budgeting. So with that said, there's a trade-off. The more life you get, the less money you're getting in your Social Security, right? So it is an issue that we have to deal with, but it is something that I do believe is manageable. So that is the final sort of thing that I'm going to say. That's the final thing that they have on the notes. So I will see y'all soon. Take care and study hard.